So I think we all recognize that oil and water do not mix. If you've ever had Italian salad dressing, you may have noticed this. You can shake those up, and it might look like they mix for a while, but as soon as you stop shaking it and you set it down, the oil's going to come up to the surface and the water's going to be on the bottom. Why does it do that? It has to do with polarity of the molecules. So there's something about the water molecules that causes them to bunch together, to hold together very tightly in one region, basically excluding the oil. The reason the oil is on top instead of being on the bottom is that the oil is less dense, and so it floats. There are other substances that do not mix with water that will sink to the bottom because they're more dense. So if we look at the Lewis structure for a water molecule, when we draw it like this, we think, oh, yeah, it's linear. But we just learned that no, it isn't. This has a bent shape, doesn't it? Because we've got these two lone pairs. And to top it off, the oxygen is sharing a pair of electrons with the hydrogen, but it's not sharing them equally. Okay, the oxygen is hogging the electrons. It's taking more than its fair share. So it's like when you see the 13-year-old sharing with the 5-year-old, and he gives the 5-year-old the little part of the cookie, right? Thinking he's not going to notice. The little guy is kind of losing out here. So we have to talk about electronegativity. Electronegativity is a fancy word. It just means the ability of an element to attract electrons within a covalent bond. So in a covalent bond, if one atom is more electronegative than the other, it's going to hog the electrons. The electrons are more attracted to it. Yeah, okay, I'll get to the analogy there. So in the water molecule where the oxygen is taking more of the shared pair of electrons, that's because oxygen is more electronegative than hydrogen. So those shared electrons are going to be closer to the oxygen than they are to the hydrogen. Electronegativity is just a relative scale. There's no absolute. And so the guy that discovered it just decided that 4 was going to be the maximum. And it turns out that fluorine is the most electronegative element, so it's given an electronegativity of 4, and then we assign electronegativities for the other elements just by comparing them to fluorine. So if we look at an oxygen-hydrogen bond, and here this is to represent the density of the electrons, or the probability that the electrons are going to be found in one place or the other, we see that there's more probability of the electrons being over here by the oxygen than there is over here by the hydrogen. And I do have a stupid chemistry land analogy for this. So this shared pair of electrons, let's draw a little picture up here. So we've got oxygen and hydrogen, and there's a single bond, which means that each atom is sharing one electron, and so there's a pair of electrons here. And in chemistry land, these electrons are two little boys. And this little boy lives at O house, and this little boy lives at H house. And they're playing together. And so they're going to play at H's house or at O's house. But these houses are not the same. At O's house, they've got a big plasma screen TV. They've got Dish Network and Netflix and just every channel there is. If you're hungry, Mom will order pizza delivered for you, and they actually have a soda fountain in the kitchen. In the backyard, they've got this big swimming pool with a diving board and a slide and a trampoline. You can even jump on the trampoline into the swimming pool. Just a fun place. So what do they have over at H's house? They've got a little TV with an antenna, and if you're hungry, Mom will make you a peanut butter sandwich, not even jelly, and she'll give you a glass of water. They've got a sprinkler in the backyard. So where are these two little boys going to spend more of their time? At H's house or at O's house? They're going to spend more time at O's house. Why? Because it's more attractive to little boys. Okay? Oxygen is more electronegative, it's more attractive to the electrons, and so they're going to spend more time over here. And we see that in this diagram down here. These electrons spend more time over here at oxygen's house than they do at hydrogen's house. And this gives us a charge imbalance. Okay, it's not that we have an ion situation here. If it was ionic, then this little boy would actually disown his family and become adopted by oxygen and live here permanently. That would be an ion. That's not what's happening. This little guy still lives over here. He still loves his mom, and they go over there occasionally. So they do go over here once in a while. He needs to change his clothes, brush his teeth, say hi to his mom. But then they go back over here because it's more fun, right? So it is shared, but there's this charge imbalance. And so we use this. This is the lowercase Greek delta. So it's similar to our D, but it's all curvy. So this delta minus means that there's a partial negative charge. It's not a full -1 charge like you would get if you gained an electron. It's a partial charge. And we don't care what part of 1 it is. It's just between 0 and 1, it's a partial charge. And on this side, then, we're going to have a partial positive charge. But that makes this bond lopsided. So this is a polar bond because one end is different than the other. And we call this a dipole moment. It's just I'm not exactly sure where the moment came from, but it always reminds me of, people say, oh, I was having a senior moment. You lost your keys or something, right? It's a dipole moment. It's a separation of charge within a bond. Any questions? Personally, I'd like directions to O's house because I'd like to go hang out there too. So covalent bonds that have a dipole moment are called polar bonds. What do you think about when you think about the word polar? Opposites. That's good. I talked about this yesterday and someone said, bears. Yeah, polar bears. But where do polar bears live? At the North Pole, right? We have a North Pole and a South Pole on our planet, and they are opposite. They are on opposite sides of our spherical Earth, but there's also a difference having to do with magnetic fields. A compass will point to the north because there's this magnetic field thing going on with our planet. And the North Pole is magnetically different than the South Pole. So when we talk about a polar bond, we have a bond whose ends are different. Okay, so polar covalent bond. The greater the electronegativity difference between those two elements, the greater the dipole moment. So the greater the difference between those two houses, the greater the difference between the time the children spend at one house versus the other. If there was just a little bit of difference, the time would be shared more equally. If there's a little bit of electronegativity difference, then the electrons are shared more equally. This is a table showing us electronegativity values for the main group elements. And we see that here's fluorine up here with a 4.0. He's the most electronegative. So fluorine is the coolest house for little electron boys to be hanging out at. And as we move away from fluorine, if we're going down a group, the electronegativity decreases. And if we go across a period backwards, moving away, it goes down. That's a general trend. We see that hydrogen, of course, has to be an exception to everything. And he pops up there in the corner. So the table is helpful, and I think there's probably some homework questions that you will need to consult the table for. On the exam, we're not going to use this table. I just want you to remember that fluorine is the most electronegative, and whoever's closer to fluorine is more electronegative than the one that's farther away from fluorine. So I suppose you could draw an analogy with a town, and this is the rich neighborhood where the houses are really fun to play at, and as you move away, the houses get less and less, the families have less money, and so there's just not as many fun toys. Of course, toys is not the only reason why children play. It's also, is mom nice or is she yelling at you? But we'll ignore that for this. So if you have two elements that have the same electronegativity, the electrons will be shared equally, and there's no dipole moment. So that's called a nonpolar bond, because the two ends are the same. It's nonpolar. If you have two atoms of the same element, here chlorine and chlorine, of course their electronegativities are going to be the same. So anytime you have two atoms of the same element, that's going to be a nonpolar bond. You can have nonpolar bonds between elements that are not the same. Let's go back to that table real quick. Let's find one. So let's see. I know there's here, sulfur. Oh, that's not what I want. I didn't want to do that. Sulfur has a value of 2.5, and carbon has a value of 2.5. They have the same electronegativity, so if you had a carbon-sulfur bond, there's no difference. It's going to be nonpolar. So that can happen, but what I want you to remember is if the elements are the same, it's nonpolar, and usually if they're different, we can assume that it's polar, and so that's what we're going to do. We're just going to kind of go with an either or. If there's a very large electronegativity difference, then the electron gets completely transferred and the bond is ionic. And this happens between metals and nonmetals. And so that's something we've already learned. If you have a metal and a nonmetal, you're going to have an ionic compound. So we can remember that even without looking at electronegativity differences. But this happens because the difference in electronegativities is especially large. And so that forms an ion. In between the identical atoms and the big difference between a metal and nonmetal, in between we have these polar covalent bonds, where the electrons are shared, but they're not shared equally. And so here we have an example of hydrogen fluoride. Hydrogen and fluorine have different electronegativities, so the fluorine has a more negative end of that dipole moment, and the hydrogen is the more positive end. Any questions? It's either so clear or so not clear. That's what no questions means. So there is a continuum between these extremes. So on one extreme you have the pure or nonpolar covalent bond where the electrons are shared equally. No difference. And on the other end you have a large difference where you have an ionic bond. And then there's the in-between. And so we have set up kind of arbitrary lines here where we decided, okay, up to a difference of 0.4, we're going to call that nonpolar. And if the difference is between 0.4 and 2, we're going to call it polar. And if the difference is over 2, we're going to call it an ionic bond. But that's just kind of arbitrary. And so you might need to refer to this, like I mentioned, for some homework problems, but we won't do this on an exam. On an exam, I want you to look at them. If they're the same atom, from the same element, then you say it's nonpolar. If it's a metal and a nonmetal, this is the metal and nonmetal, it's going to be ionic. And if you have two different nonmetal elements, I want you to say that's probably polar. Okay, that's what we're going to go with. So let's do an example. Let's look at these different combinations and identify whether this is pure covalent. I prefer to say nonpolar. Pure covalent, meaning nonpolar. Is it polar covalent or is it ionic? So between iodine and iodine, that's going to be nonpolar because those are the same. So nonpolar covalent. How about between cesium and bromine? Well, find them on the periodic table. It's going to be ionic because cesium is a metal. Cesium is a metal, bromine's a nonmetal. Metals and nonmetals always form ionic compounds. How about phosphorus and oxygen? Polar covalent. Two nonmetals, they're not the same. So polar covalent. So this is the level of question that I would ask you on an exam. Not asking you to look at the table and do subtracting and compare to this guideline and stuff like that. So bonds can be polar, molecules can also be polar. But just because you have polar bonds in a molecule does not mean that the whole molecule is polar. A polar molecule is going to have a net dipole moment. That means that the polar bonds are going to add together instead of canceling out. With a diatomic molecule, it's much easier to think about. A diatomic molecule has two atoms. It has one bond. If the bond is polar, the molecule is polar. But when we have more than two atoms, we have to consider the geometry of the molecule as well as the polarity of the bonds. So carbon dioxide, here's the Lewis structure for carbon dioxide. Here we have oxygen and carbon. Those are two nonmetals, right? But they're not the same element, so we're going to assume that that's a polar bond. We can indicate that bond being polar with an arrow. The arrow points to the more electronegative element. It's like somebody comes over and says, "Where did Johnny and Tommy go?" And they point to the house that's cooler, right? They went over there. So the arrow points to the more electronegative element. And on the periodic table, when we look at that, we find oxygen being right next to fluorine and carbon being a couple over from fluorine. Oxygen is closer to fluorine, and so we can predict that it's more electronegative. The plus sign on the other end of the arrow indicates that this is the positive end, and the arrow is pointing to the negative end. So this bond is polar in this direction, and the other bond is polar in the opposite direction. They are the same amount of polar because it's carbon-oxygen and carbon-oxygen. So this is a little bit like someone playing tug-of-war. For those of you who like math, what this is vector addition. Vector addition in three-dimensional space. But I'm guessing most of you are not fond of vector addition. So you can imagine that we've got people playing tug-of-war here. And so this guy's pulling this way, the guy in the middle is holding both of the ropes, and this guy's pulling that way. What's going to happen? Are they going to move? No. Hopefully these guys aren't so strong that they pull this guy's arms off, but there's going to be no net movement. They're equal and opposite, and so they cancel out. So this molecule is nonpolar even though it has two polar bonds, because we don't have one end being negative and one end being positive. Both of the ends are the same, and it's symmetrical. So the molecule is nonpolar. And the polarity of the molecule is very important for its chemical and physical properties. So we can represent those bonds as arrows that point in the direction of the negative pole, plus sign at the positive, and if they are in exactly opposite directions, they cancel out. So let's look at water. We've talked about water today and how it has a bent structure, right? Because there's actually two lone pairs there. That's what's causing it to be bent. And each of these bonds is polar, oxygen being more electronegative, and so we have a dipole moment going this way and a dipole moment going that way. And those are not going to cancel each other out. So if we think about playing tug-of-war, we've got a guy here, and we've got a guy over here, and a guy over there. This guy is stronger. He's the more electronegative. He's got some crazy hair going on there. He's playing tug-of-war. This guy's pulling at an angle, and this guy's pulling at an angle. Are the three of them going to move? They're going to move in that direction. They are, yeah. So let's get rid of these guys, because the tug-of-war thing works for some people, not for others. It's fine. So let's think about these guys, these dipoles, as having two components, a vertical component and a horizontal component. And so horizontally, it goes like that, and this one goes like this. And then vertically, it would go from here to there, and from here to there. So this is a little bit like traveling on in a town where the streets are laid out on a grid, right? And to get from this point to that point, you can't go diagonally through people's yards. You have to go in the street with your car. So you go over 3 blocks this way, and you go up 3 blocks that way, right? That's what we have to do. And you end up in the same place as if you flew over. So when we divide it up like that, then we can look and see, well, this arrow and that arrow, those are going to cancel each other out, aren't they? Because they're equal and opposite in direction. It's like +2 and -2. But these blue arrows are both going in the same direction. And so overall, what we end up with is movement in this direction. So there's vector addition in a nutshell.
We can just say if the electronegativity is pointing in the same direction, it's going to be a polar, more like a polar bond, and if it's pointing in the direct opposite direction, it's non-polar.
Pretty much. So I'm explaining this all, and then I'm going to give you a shortcut at the end. I would really like you to understand the why behind this. And so here what we see is that they are not canceling each other out like they did for the carbon dioxide. If they don't cancel out, then there will be a polar molecule. And the more three-dimensional and complicated it gets, the harder it is to see if they're canceling out or not. This one at least is still planar. But water is a polar molecule. So these are common cases. If you have two identical bonds in a linear shape, they're going to cancel each other out. If you have a trigonal planar shape with 3 identical bonds, those are also going to cancel each other out. If you think again about playing tug-of-war and you've got one guy pulling this way and one that way and one this way, this guy is just going to be pulled around, but he's not going to actually move. These two situations where you have a bent molecule or a trigonal pyramid, you're going to have net movement, and these are going to be polar. Over here where we have a tetrahedral shape for the molecule with identical bonds, that's going to be nonpolar, because those are opposing forces. So how to determine whether a molecule is polar? Well, first of all, does it have polar bonds? The bonding atoms have to have different electronegativities. And like I said, we're going to pretty much ignore those cases where you can have 2 different elements of the same electronegativity. So if there's different atoms, different elements involved, you can pretty much assume the bonds are polar. Then, to determine if those add up to a net dipole moment or if they cancel each other out, you need to think about Vesper theory and the shape of the molecule. We got to have the shape. Because water and carbon dioxide on the surface look very much alike, but because of the shape of the molecule, one being linear and one being bent, one is polar and one is not. And then ask yourself, is the molecule symmetrical? Okay, so here's my alternate method. Look at the Lewis structure and ask yourself, are there any lone pairs on the central atom? Are the atoms bonded to the central atom all the same, or do they have the same electronegativities? If both of these are true, it's nonpolar. That's easier, huh? Doesn't work all the time, but works most of the time. And honestly, most of the time is awesome. So let's look at CH4. CH4, what's the Lewis structure going to be? Well, we're going to have a carbon in the middle, and we're going to bond the hydrogens to it because that's the only thing we can do. How many valence electrons do we have? Carbon has 4, and each hydrogen has 4. So we got 4 plus, each hydrogen has 1. We've got a total of 8. If we put bonds, 2, 4, 6, 8. There's our Lewis structure. No lone pairs. So let's use my method. So we've got our Lewis structure. Are there any lone pairs on the central atom? No. Are all the atoms bonded to the central atom the same? Yes, they are. So there's no lone pairs, and all the atoms are the same. Both conditions are met. This is a nonpolar molecule. Now let's think about the whole pulling business. Are these polar bonds? Most likely, because carbon and hydrogen are different elements, right? So the carbon would be the more electronegative, and so this is a polar bond, and that's a polar bond, and this is a polar bond, and that's a polar bond. It's a little hard to visualize. Do those things cancel out? But this molecule is symmetrical, isn't it? Those atoms are arranged in three-dimensional space in a symmetrical way. And the bonds, dipole moments, are all pointing in the same direction, and so they're going to cancel out. So that's the more understanding method. Any questions? Let's look at NH3. Well, whoops. Nitrogen in the middle, hydrogen, hydrogen, hydrogen. 5 valence electrons from the nitrogen, 3 hydrogens, 8. We end up like this. We've already gone over all this, so I'm not going to take too much time on that. There's our Lewis structure. So let's do my method first. Are there any lone pairs on the central atom? Yes. We're done. It's polar. So then let's think about why. Well, what shape is that molecule going to have? Trigonal pyramid. Are these bonds polar? Yeah. So they have dipole moments. You see that all of these arrows are pointing in a general up direction, and there's nothing pointing down, right? If we add those vectors together, overall we have an up effect, and so we do have a polar molecule. Let's do SO2. Well, sulfur, oxygen, oxygen, 2 2 times 6 and 6, 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. So there's our Lewis structure. It's kind of a funny looking electron over there. Are there lone pairs on the central atom? Yep. So it is polar. And you're probably wondering, why on earth did you talk about just cut to the chase at the very beginning. Yeah, well. This one has 3 groups, right? Single bond, double bond, lone pair. So it's going to make a trigonal planar shape with the electrons, and then this guy's invisible. And so our shape here is bent. These bonds are polar, going from oxygen to sulfur. No, from sulfur to oxygen. Wait, I was thinking the right direction. Those aren't going to cancel each other out, are they? So, polar molecule. So back to why don't oil and water mix? Well, it's because water molecules are polar and oil molecules are not. They are non-polar. Polar molecules interact very strongly with each other because for this water molecule, one end of it is somewhat positive and the other end is somewhat negative. So the oxygen end is negative and the hydrogen end is positive. And so we get an attraction between the positive end of water and the negative end of water, just like opposite poles of a magnet attract each other. So we get this attraction between the molecules that doesn't happen in the oil molecules. And that attraction is so strong that they exclude the oil. It's a little bit like a clique in high school. You know, that group of girls that you just couldn't get into no matter what you tried because they are just so into each other they have no time for anybody else. I like this example a lot. These solid marbles are magnetic marbles. So they're going to stick together. And then we've got glass marbles that are not magnetic. And if you throw a bunch of these marbles together, what's going to happen? The magnetic marbles are all going to clump up, and they're going to push the glass marbles out. And that's what's happening with the oil and water. Because the water molecules are polar, they have this attraction. It's electrostatic, it's not magnetic, but it's very similar. They have this attraction, they're sticking together, and the oil molecules get pushed out. They can't interact in that way, and so they get excluded. Have you ever used Crisco to grease a pan? And you get Crisco on your fingers, because really there's no way to grease a pan without just dipping your fingers in the Crisco. Or you get butter on your fingers and you can rinse it off. You can try to rinse it off with water. It's not going to rinse off, will it? Or maybe for you guys who don't bake, you've got grease on your hands from working on the car, or motor oil on your hands. Water's not going to take it off, right? Because grease, motor oil, Crisco, butter, all of those are oils. They're non-polar. They do not mix with water. So how do you get grease off your hands? You use soap. Well, soap is pretty neat stuff. Here's an illustration of a soap molecule. A soap molecule has a polar end and this long non-polar tail. This non-polar tail mixes really well with the grease, and this polar head mixes well with the water. And so what they do, which there's no picture, so I'll have to draw one, is it's kind of like circling the wagons. They form what's called a micelle, with the polar head on the outside and these nonpolar tails on the inside. It's like the pioneers circling the wagons to protect themselves against the wolves or other things. So here in the middle are all of these nonpolar tails. So the grease is fine in here. So you can get small amounts of grease dissolved in here, and then you've got these polar heads on the outside that allow the soap micelle to float around in the water. And so it solubilizes the grease and allows it to wash away. And there we have the end of the chapter and all these chapter and review slides. Lots of stuff in this chapter.